consistency, which is one of the properties of point estimators. Okay, so when do we say an estimator is consistent? Okay, so consistency is a function of a variance. Okay, so we say an estimator theta hat sub n is a consistent estimator of the parameter theta. Okay, if the parameter is tending to theta, that's in probability. We call that convergence in probability. So I should have indicated here like that. So we call this convergence in probability. Okay, that's if theta converges in probability to the parameter being estimated. Okay, so mathematically we say the limit as n becomes large of the probability of the modulus of the difference between the parameter and the estimator and the parameter being estimated is greater than epsilon is equals to 0. Okay, where epsilon is any positive number. Okay, where epsilon is any positive number. So if this probability can be shown to be equals to 0 for large n, then we can say that theta is a consistent estimator of the parameter theta. Okay, that's what we call the Jeff's inequality. Okay, you can look at this and see how convergence can also, consistency can also be achieved for a given estimator. So let's use this theorem because this one is far much easier to understand and to achieve in practice. So an unbiased estimator theta for the parameter theta is consistent if its variance is equals to 0 as n becomes large. So the limit of the variance of the estimator as n tends to theta, tends to infinity, is equals to 0. Okay, so no need for the proof. Given an estimator of a certain parameter, if you can obtain the variance of that estimator and show that that variance is tending to 0 as n tends to infinity, where n is the sample size obtained from the population that has got that parameter being estimated, then we can say then the estimator is consistent for the parameter theta, for example. So let's check this. Example number 1. So let y1, y2 up to yn be a random sample of size n from a population with mean mu and variance sigma squared, which is finite. Okay, then we want to show that y bar, which is given by 1 over n, the sum of yi's, is a consistent estimator of theta. Okay, of course, that's the definition of this is the definition of the sample mean. You are simply summing the yi's for all the values I from 1 to n by n. This is actually the sample. That's the sample mean. So we want to show that y bar is a consistent estimator of the parameter mu. So you remember we said sample mean is an estimator of, is an unbiased estimator of the parameter mu, which is the population mean. Okay. So can we get the, first of all, whether value of y bar, okay, is equals to the expected value of 1 over n, the sum of yi's, for all the values of I from 1 to n. So this is equals to 1 over n, the sum of the expected values of yi's, I from 1 to n. And we are told these yi's are random samples obtained from a population with mean mu. So this is equals to 1 over n, the sum I from 1 up to n of mu. Expected value of yi is mu. So this is n mu divided by mu. So expected value of y bar, which is the sample mean, is equals to the population mean mu. So we can conclude and say the sample mean is unbiased. That's an unbiased estimator for mu. So you remember the unbiasedness. We said unbiasedness is given by the expected value of the estimator minus the parameter being estimated, which is equals to expected value minus theta. So this is equals to 0 if the estimator is equals to the parameter being estimated. So we've shown that the estimator is unbiased. So we want to proceed and check whether the estimator is consistent. So consistency is a function of variance. So we said the limit as n tends to infinity of the variance of a given estimator, say theta sub n, is equals to 0 if the estimator is consistent. Okay. If we cannot show that the variance is tending to 0 as n becomes large, then we cannot prove that that estimator is consistent. Okay. So we get the variance of y bar, okay, which is equals to the variance of 1 over n, the sum of yi's, I from 1 to n. Okay, so you get the variance on both sides of the equation. So this is going to be 1 over n squared, using the linear properties of variance, 1 over n squared times the sum of the variances of yi, all the values of y from 1 to n. Okay, so this is going to be 1 over n squared. That's 1 over n squared times the sum I from 1 to n. Okay, the variance of yi, that's sigma squared. Okay, so we are summing sigma squared n times. Okay, so that is to say you have sigma squared plus up to the nth time by n squared. So this is equivalent to n sigma squared divided by n squared. Are you following what I'm doing? Yes. So we have the variance of y bar is equals to n sigma squared over n squared. So this is sigma squared over n. Are we together, class? Are you following what I'm doing?
Yes.
Okay, so we can now apply.
Please, could you repeat?
Yes, Makayanga.
Could you please repeat?
From where?
From where you started writing.
What's happening
after where you wrote?
with your speakers? Your speakers are not in very good shape.
Can you hear me now?
You want me to repeat from where? Oh, it's really terrible. Okay, I'm getting what you are saying, but the speakers are not good. So you want me to repeat from where?
From where you started with the variance.
Oh, with the variance.
Yes.
Okay, thank you. Okay, so this is what we said as far as consistency is concerned, that if we want to show that the estimator theta, call it theta hat sub n, okay, is consistent for theta, then we simply get the variance of this estimator and show that this variance is tending to 0 as n tends to infinity, as n becomes large, as the sample size becomes large. So what we really want to show is just to say the limit as n becomes large, as n tends to infinity, of the variance of theta. This is in general. If we can show that this is equal to 0, then we can conclude that this estimator here for theta is consistent. Okay. So in this case, the estimator we are using is just that of y bar. So we want to show that the limit as n becomes large of the variance of the sample mean is equals to 0. That is what we want to show. Are you getting me, Makayanga?
Yes.
Okay. So can you mute yourself, please? So that's what we've done all along from here. So I don't know, maybe I can, so we're saying y bar is given by 1 over n, the sum of yi's, I from 1 to n. So we want to get the variance of y bar. So then we take the variance on both sides of the equation like this, okay? For all the values of y's, y from 1 to n, like this. So n is a constant, okay? That's the sample size. So you remember we said the variance of ax is equals to a squared times the variance of x. You remember that, Makayanga? So where a is a constant, so if we say the variance of a third x, that's the same as a third squared times the variance of x, because a third is also a constant. The variance of 1 over n times x is equals to 1 over n squared times the variance of x. This is from the linear properties of expectation and variance. Okay, so we are here. Okay, so we take the variance on the right hand side. So we have 1 over n squared, okay, times the variance of the sum I from 1 to n of yi, like this. So again, because of the linearity of variance and expectation, that is the same as 1 over n squared, that is for this, times the sum of the variances of yi. So we take the variance inside the summation sign. So we have this is 1 over n squared, okay? 1 over n squared times the sum I from 1 to n. The variances of yi, we are told that the sample yi, okay, I from 1 to n, this is obtained from a population with mean mu and variance sigma squared, okay, which is a finite variance less than infinity. That's what we are told in the question, okay? So the variance of each yi is equals to sigma squared, okay? So we are summing, sigma squared is a constant. So you are summing a constant n times, say 4 plus 4 plus 4, like 6 times. So is that the same as 6 times 4? So 4 plus 4 plus 4 plus 4 plus 4. How many times? 6 times. Is that the same as 6 plus 4, Makayanga?
Yes.
So we are summing sigma squared n times. So that is n times sigma squared, okay, divided by n squared, okay. So we can simplify that fraction so that we have 1 n cancels with 1 n here. So what remains will be sigma squared over n, okay. So is that clear now?
Yes, yes. Thank you, sir.
Okay, welcome. So what we have now is to show that this variance is tending to 0 as n becomes large. Okay, so we want to show that the limit as n tends to infinity of the variance of y bar is equals to 0. So is that the case? So what's the variance of y bar? Y bar. So limit as n tends to infinity of sigma squared by n. What shall we get? What happens as the denominator becomes larger and larger while the numerator remains constant. Let's start with a half, 1 over 2, that is 0 0.5. 1 over 10, that is 0 0.1, 0, 1. What about 1 divided by like 100,000? 0 0.00001. You see what happens as the denominator increases. The values are tending to 0. Are you seeing that? Yes. So you can see the denominator is increasing from 2 to 10 to 1,000 to 100,000, can go to 1 million. So I'm only demonstrating what happens as the denominator tends to infinity, as n tends to infinity. Are we together, class?
Yes.
Yeah, so is it easy to see that this variance is tending to 0 as n becomes large? If
Yes.
that is so, then we can say therefore y bar, okay? We can say therefore y bar is a consistent. You can conclude and say therefore y bar is consistent, okay? For mu, it is consistent in estimating the parameter mu, okay? So there are so many techniques of looking at the properties of variance, properties of estimators. So that's one of them, looking at the consistency, checking the unbiasedness of the estimator. If all of them are unbiased, then which one has got smaller variance compared to the other? So that is that. So you can see this variance is tending to 0 as n becomes large. So you can conclude and say y bar is a consistent estimator of the parameter mu. So remember, we are estimating the population parameters using the sample characteristics. Y bar is a sample characteristic. Mu is a population parameter. So we have two main techniques of finding the estimators of finite population parameters. One is what we call the method of moments. Number two is what we call the method of maximum likelihood, or we call it maximum likelihood estimation, MLE. Okay, this stands for max. Okay, we start by looking at the method of moments. So we are saying this for one or more parameters of a statistical model. It's one of the oldest techniques of the deriving point estimators, but still they can enable us to find one or two properties of the estimators. So let's make this recall. The kth moment of a random variable is given by mu k, which is the expected value of y to the power of k. You recall this even from the moment generating functions. We mentioned that the kth moment of a random variable is denoted by mu sub k, which is equal to the expected value of y to the power of k. What this equation simply means is that when k is equals to 1, then you have mu sub 1, which is expected value of y to the power of 1. So this is simply what? This is simply the expected value of y. Is that clear? When k is equals to 2, then you get the second moment about the mean. That's when k is equals to 2. So mu 2, which is equals to expected value of y squared. Are we together? Yes? Yeah, so you see, the second moment can be given a function of variance. Expected value of y squared, okay, minus expected value of y all squared, or the square of the expected value of y. So the variance of y for example, is given by mu2, okay, minus the square of the first moment. You can generate those other moments as a function of what's already given. So the corresponding kth sample moment is given by m sub k, which is equals to 1 over n, the sum of yi to the power of k. So let's take an example. If k is equals to 1, then we are talking about m1, which is equals to 1 over n, the sum I from 1 to n of yi. So yi to the power of 1, that's simply yi, isn't it? So what is this? Is this the sample mean? Yes. Is it easy to see that that is the sample mean? When k is equals to 1 in this equation. Are you getting what I'm saying? Okay, so we are saying mk is an estimator of mu k. You see, mk is what we call the sample moment. Okay, so we use the sample characteristics to estimate the finite population characteristics. Mu sub k is that's a population characteristic. Okay, so that's okay. So let's proceed. So the estimator based on the method of moments will be the solution to the equation mu k is equals to mk. Okay, so for example, when k is equals to 1, then we equate mu1 is equals to m1. We also get when k is equals to 2, what's the function? Then mu2 is equals to m2, like that, up to mu k is equals to mk. So we are saying the estimator based on the method of moments, m or m, okay, will be the solution to this equation. That's equation number 1. So let's take the first example. I from 1 to n be a random sample obtained from a uniform in the range 0 to theta. So we want to use the method of moments to estimate theta. Okay. So what is the expected value of yi? You remember uniform distribution generally in the range AB? You remember this? You said the expected value of x was obtained as a plus b over 2. You remember that? And the variance of x, we got this as b minus a squared divided by 12. Okay. So in this case, we are told yi as a uniform distribution in the range 0 to theta. So what is the expected value of yi? Yes, it is the lower limit or the lower bound plus the upper bound, that's 0 plus theta divided by 2. So we get theta over 2. Are you seeing how we are getting this?
Yes.
Now, see, when you remain silent, or you are offline, are you seeing how we are getting this expected value of yi? Now, the variance of yi is given by b squared, okay? B squared minus b minus a squared divided by 12. So in this case, we have theta minus 0 squared divided by 12. So this is theta squared by, that's theta squared by 12. Okay, so that's how we are getting those values of the expected value and variance of y. Okay, so you remember what we mentioned earlier? We said mu k. Okay, we said mu k is given by 1 over n, the sum I from 1 to n of yi to the power of k. So when k is equals to 1, then we have mu1 is equals to 1 over n, the sum I from 1 to n of yi to power 1, like that, which may not be necessary to write. Okay. So is that okay? So we said the solution to the equation mu k is equals to mk will give us the method of moments, estimator. Okay. So we're saying therefore mu1 is equals to m1. Okay. So expected value of yi is equals to mu1, which is equals to theta by 2. Okay. So I hope you are following this discussion. So then M1, we said M1 is given by 1 over n, the sum of yi I from 1 to n to the power of 1, which is y bar, okay, which is what we have here. Then mu k, we said that's the same as expected value of yi to the power of k. So we want to equate mu k is equals to mk when k is equals to 1. So mu1 is equals to m1. So what do we get? What is mu1? It's theta over 2. What is m1? It's y bar. Okay. So we have theta for the so we want to check whether that estimator is unbiased or otherwise, and even the consistency. So if you want to know if this estimator is unbiased, okay, then you get the estimator, the expected value of the estimator, compare with what we have on the right hand side. Then we have expected value of theta is equals to 2 times the expected value of y bar. Again, from the linear properties of expectation, when you say expected value of 2x, 2 is a constant, so you say 2 times the expected value of x, which is what we are doing here. Take the expected value here, expected value here. So this is 2 times the expected value of y bar, which is theta over 2. Okay, so you get theta. So that means theta is an unbiased estimator for the parameter theta that's being estimated. Okay, so again, you want to find out whether this estimator is consistent. Okay, so the estimator is given by theta hat is equals to 2y bar. So variance of theta hat is equals to the variance of 2y bar, okay, which is equals to 2 squared times the variance of y bar, okay. And what is y bar? So 2 squared is 4, so you have 4 times the variance of 1 over n times the sum of yi for all the values of y from 1 to n. That is y bar, okay. So this is 4 times 1 over n squared, okay, times the sum I from 1 to n of the variances of yi, okay. And what's the variance of yi? Said the variance of yi is given by theta squared by 12. You saw how we got this. So this is 4 divided by n squared times the sum I from 1 to n times theta squared over 12. So the variance of each yi is theta squared over 12. So we are summing this variance n times. And you know that is a constant, okay, the following. So the variance of that estimator is equals to 4 by n squared times n times theta squared over 12, okay. we are summing theta squared over 12. How many times? N times. Okay. So by 4 is 1, by 4 is 3, by n is 1, by n is n. So what do we have as the variance of theta? It's theta squared by 3n. Is that correct? Is that correct?
Yes.
Okay. So we want to take the limits. Okay. We want to take the limits as n becomes large, as n tends to infinity. Then what do we have there? Okay. So we say the limit as n tends to infinity of the variance of the estimator is equals to the limit that's equals to the limit as n tends to infinity of theta squared over 3n. So you can see the numerator is constant. The denominator varies for different values of n. So as n becomes large, the denominator becomes larger and larger. So will that tend to 0? Yes. So then we say that limit, the limit as n tends to infinity of the variance of that estimator is equals to 0. So therefore, this is consistent. That estimator is consistent for the parameter theta. So that's how to check or how to show consistency of a given estimator of the parameter. So we conclude that theta is consistent because you can show that that variance is tending to 0 as n tends to infinity. Okay. That's okay. So yes.
It's okay.
So let's take a short break of 10 minutes break. Okay. 10 minutes break, then we continue. Thank you. continue, class.
Okay.
Can we continue? Okay. So let's look at example number 2. So let yi's I from 1 to n be normally distributed random variables with mean mu and variance sigma squared. Okay. So we are saying yi as a normal distribution with mean mu variance sigma squared for the values of I from 1 to up to n. That's saying y1, y2 up to yn. Find the method of moments estimators of the parameter mu and sigma squared, which is the population variance. Okay, so using the method of moments, the solution is given by solving this equation. Mu k is equals to mk, where mu k, this is the kth sample, mk is the kth sample moment, this is the population sample, that's the population moment. I'm sorry. So mu1 is given by expected value of yi. That's from mu k is equals to expected value of yi to the power of k. So when k is 1, then we have mu1, which is expected value of yi, which is given by mu here. Okay. Then mu2 is given by expected value of yi squared. When k is equals to 2, then we have mu2, which is expected value of yi squared, like that. And this is a function of what? That's a function of variance. You know, to get variance of x, that's given by expected value okay, if we are doing, then variance of y squared minus the square of general. Okay, so so you can say sigma squared is equals to the expected value of y squared minus the square of the mean. Okay, and the mean is mu, so minus mu squared. So we can have y on one side of the equation, you make it the subject of the formula. So expected value of y squared is equals to sigma squared plus mu squared. These are yi's, these are yi's, these are yi's. The normal random variables. Are you seeing how we are getting this?
Yes.
Yes. Is that clear? Yeah.
Yes.
So that's how we are, yeah, that's how we are cutting this. That's how we are making this argument here. Then we said mk, the kth sample moment, is given by 1 over n, the sum of yi to the power of k. So when k is 1, then we have 1 over n, the sum of yi, that is y bar. Okay, that is equals to y bar. So I believe that is clear. M2, okay, M2 is given by 1 over n squared. That's from mk is equals to 1 over n, the sum of yi to the power of k. So when k is 2, then we have m2, 1 over n, the sum of yi, the sum of yi squared. Okay. So you remember we said the solution under the method of moments is given by the solution, the equation mu k. This equation number 1 here, the estimator based on the method of moments will be the solution to this equation here. Okay. So where were we? Yeah, we are here. Okay. So M1, mu1 is mu. So that is the estimator. That's the estimator of the, so the sample mean is said to be the estimator of the finite population mean, mu, or the estimate of the finite population mean, mu. So you can check for unbiasedness by taking the expected values on both sides of the equation. Then when k is equals to 2, then what is this equation? Mu k is equals to mk. Then you say mu2 is equals to m2, okay, which is actually a function of the variance, okay. So the estimator of the population variance, okay, is given by the sum 1 over n yi squared minus y bar squared. So the reason why we are replacing here mu with y bar is because this is an unbiased estimator. The sample mean is an unbiased estimator of the population mean. So you can simply substitute. This is the square of the mean. So when you check the expected values on both sides, you'll realize that the expected value of the population variance is not equals to the expected value of the estimator of the population variance is not equals to the variance of the population. So we say this is a biased estimator for sigma, actually for sigma squared here, okay. So you can also check for consistency, if that is a consistent estimator of the population. And do we have instances where an estimator is unbiased, okay, but it's not consistent, unbiased and not consistent? So you check for that. So the other method of finding estimators is what we call the MLEs, maximum likelihood estimators, or a maximum likelihood estimation, okay? So suppose the likelihood function depends on k parameters, theta 1 to theta k, okay? Then we choose as estimates those values of the parameters that will maximize the likelihood function. That's what we mean by the maximum likelihood. We are looking for the estimators or the values of the estimates, okay, that will maximize the likelihood of a given parameter, okay. So capital L here, this is what we call the likelihood. That is what we call the likelihood function here, okay, which is given by the conditional conditional function of y1, y2 up to yn, given the parameters theta 1 to theta k, okay. So it's a conditional function. The likelihood for y1, given that the parameter under consideration is theta 1, the likelihood y2 given the k, we call that the likelihood function. It's much friendly to maximize the logarithm of the likelihood function as opposed to the likelihood function itself, okay. So we're saying the small l of theta is given by the natural logarithm of the likelihood function, okay. This is what we call the log likelihood function, meaning the logarithm of the likelihood function of a given parameter. So we are saying the likelihood function and the logarithm of the likelihood function, they have their maximum values at the same value of theta, but it's normally much easier to maximize the logarithm because of friendly manipulations that we can do. So that's in general sense what we mean. So the small l of theta is the natural logarithm of the likelihood function. So let's take a look at this example here. This is a binomial experiment consisting of n trials, okay, with observations y1 to yn, where yi will return a 1 if the ith trial is a success, and it will return a 0 if it's not a success, okay? I mean, if it's a fail. So we are told to find the maximum likelihood function of the parameter p, that's the probability of success. So this probability function here can be interpreted to mean a Panoli experiment. So you remember the connection between Panoli experiment and the binomial experiment. If you repeat the Bernoulli experiment n times, then you'll get binomial experiment. You remember these guys? X as a Bernoulli distribution with parameter P, which is the probability of success. You remember its PMF. This was given by 1, okay, or P if it's a success, 1 minus P if X is 0, when X is 0, okay? And this is when X is 1, or its PMF is given by what? P to the power of X, 1 minus P to the power of 1 minus X. But if X has a binomial distribution with parameters N and P, then you remember how the PMF looks like. N choose X, P power X, 1 minus P power N minus X. So you can see the only difference between these two is that we are repeating this experiment how many times? N times, okay? So that's why we are saying that function here, or that indicate a variable yi can be interpreted to mean a Bernoulli experiment. So yi as Bernoulli experiments with probability of success P, okay, where yi is such that it's P, or it's 1 if it's a success, and it's 0 if it's failed. Okay, and we are doing that n times, transforming that into a binomial random variable, okay, which can be represented by the likelihood function capital L of P, okay. So this is the probability that we have y1 given that it's a success, probability that we have y2 given that it's a success. You see, I is taking values 1, 2 up to n. Okay, this goes to up to yn if there is a success being observed. Okay, so this one can be condensed into p to the power of y. Okay, 1 minus p to the power of n minus y. Okay, that's what we call the likelihood function for this particular experiment here. Okay, so we can take the natural logarithm of the likelihood function. So we get L small l of p as the natural logarithm, call it ln of the log likelihood of the likelihood function L of p. Okay, but here we are defining y as the sum of the yi's, which is the number of times we observe a 1. In other words, the number of successes observed from that experiment. Okay. So we have the likelihood function, okay, as p to the power of y, 1 minus p n minus y. So when we take the logarithm on both sides of this equation, okay, then we have what we call the small l of b, which is equivalent to this. So in other words, we are saying L of p is equals to, when you introduce logarithms here, okay, when you have, say, y is equals to x squared. So when you introduce logarithms, so you have log y, that's the same as logarithm of x squared. So if they are to base 10, then that's the same as 2 times the logarithm of x. You remember those logs, isn't it? So when you introduce logarithms here, natural logarithms, you see that's a multiplication. Or if you have y is equals to ab, okay, then you introduce logarithms, for instance, to base 10, or if on the natural logarithm. So natural logarithm of y, that will be equals to the natural logarithm of a plus the natural logarithm of b. If it's a multiplication and you introducing logarithms, you understand? Are you getting what I'm to the power of y, 1 minus p raised to n minus y, okay? So when you introduce natural logarithm on both sides, you see this is a multiplication in between here, p to the power of y times this, okay? So that changes to y, or a natural logarithm of p to the power of y plus natural logarithm of 1 minus p to the power of n minus y. So that is equivalent to saying y times the natural logarithm. So the power becomes the coefficient here plus, okay, n minus y times the natural logarithm of p, okay? So we are going to take the first derivative of the log likelihood function with respect to the given parameter, okay? So you remember from your calculus, when you have y is equals to natural logarithm of x, then dy over dx, is it the same as 1 over x? Do you remember? Yeah, so when we differentiate this term here with respect to the parameter p, okay, then we have, this is y over p, okay, y over p. Then we also differentiate, so we have y is equals to natural logarithm of 1 minus p, okay? So dy over dx, okay, or y prime. So what will that give you? Negative 1 over 1 minus p, isn't it? Because of this negative here. So we have minus n minus y divided by 1 minus p. That's what we have. So we make p the subject of the formula, okay? What will that give you? You remember the first derivative, the first derivative of a function, that will give us the gradient function. That's always equals to 0, okay? The gradient function, if you can recall your differential calculus, okay? So the first derivative is equals to 0. The second derivative is equals to what? You remember those derivatives? When you differentiate this guy with respect to p, then the first derivative is equals to 0, okay? So that's what we are doing here. So that we say y over p minus n minus y over 1 minus p is equals to 0. So y over p is equals to n minus y over 1 minus. So y into 1 minus p, okay? So y minus yp is equals to np minus what? Minus py. How can you make b the subject of the formula? So of course, you see this guy, this one, and this one cancels, okay? So you have y is equals to np, okay? So p, which is an estimator of the probability of success, is given by y. Under the maximum likelihood estimation, we want to know at which point do we have the estimator being maximum, okay? So what we do, we check the second derivative. We check the second derivative of the MLE, okay, or of the natural, natural logarithm of the likelihood function. Check the second derivative if it's less than 0 or greater than 0. So if the second derivative of the log likelihood function is less than 0, then it means the first derivative is maximum or is larger than the second derivative, okay? So here we differentiate this function once again, this one here, with respect to p, okay? So that is L prime of p, that's equals to, you can say yp to the power of minus 1 minus n minus y like this, into 1 minus p to the power of -1. That's equivalent to this. Yes? Mean when you say y is equals to 1 over a, is that the same as a to the power of -1? That's what we are doing here, okay? So that we can easily differentiate. Or you can use any method of differentiation to carry out to get the second derivative of this. So when you differentiate this function here with respect to p, so first of all, we have this negative here times y times p raised to -2. The power decreases by 1 after differentiation. So minus, so you print this minus, so minus, that is -1, okay, like this, into, when we differentiate this term with respect to p, then we get -1, okay, times this minus here, this one, okay, then into n minus y times 1 minus p to the power of, so the power reduces by 1, so we have -1 minus 1, which is -2, okay? So what do we get? So we get the second derivative L prime prime of p will give us, this is negative y divided by p squared, okay? Minus a minus times a minus times a minus is a minus, okay? So n minus y like this divided by 1 minus p squared. So is this term less than or equals to or greater than 0? Is it less than 0 or greater than 0? Definitely for any value of p and n, that is less than 0 because of these negatives here, here and here. That is less than 0. So if the second derivative of the log likelihood function is less than 0, likelihood function must be the maximum. So in that case, we say the maximum likelihood estimator of the parameter p, which is the probability of success, is given by this estimator, which is y out of n. So this is maximum because the second derivative is less than 0. Is that okay?
Yes.
So maybe we look at another example. We look at another example somewhere, okay? So maybe we should have added here that the first derivative, we differentiate the log likelihood function with respect to parameter theta, okay? So before I give you these notes, then first of all, the partial derivative of L of theta, okay, with respect to theta, this is equals to the first derivative of the natural logarithm of the log likelihood function with respect to theta. So we want to show that if this one is maximum or otherwise. So for us to know whether the first derivative will give us the maximum value of the estimator, then we get the second derivative, the squared natural logarithm of the log likelihood by d theta squared. Then we check, is this less than 0 or greater than 0? So it is the second derivative that will enable us to know if the first derivative is maximum or otherwise, okay? So example number 2, so let yi I from 1 to n be iid, that is identically and independently distributed normal random variables with mean mu and variance sigma squared. Find the maximum likelihood estimates of mu and sigma squared. Okay, so first of all, you write down the log, the likelihood function of the parameters. So you know the PDF of the normal distribution looks like. Okay. So if yi has a normal distribution with mean, mu, variance, sigma squared, then you know f of y is given by 1 divided by the square root of 2 pi sigma squared times exponent of negative 1 over 2 sigma squared into about the likelihood function. Then we are getting this PDF of mu sigma squared is given by and sigma squared. These are the two parameters under the normal distribution up to f of yn given mu and sigma squared. Okay. So when we multiply that, then we have 1 over sigma or 2 sigma squared to power n. Okay. That's n times that likelihood function. Okay. Times exponent of the sum I from 1 to n yi minus mu squared by 2 sigma squared. So in summary, we have the likelihood function of the parameters mu sigma squared as 2 pi sigma squared to the power of n by 2. Okay, exponent of negative summation I from 1 to n yi minus mu. So how do we get that? How do we have this? So this is, we're saying 1 over 2 pi sigma squared square root to the power of n. So this is equals to 1 divided by 2 pi sigma squared raised to a half. Okay, raised to a half like that, all raised to power n. So we said when we say 1 over a, that's the same as a raised to negative 1. Then if you have 1 over a squared, 1 over a raised to a half, that's the same as a raised to negative a half. Are these correct? Yes. So that this one is equals to 2 pi sigma squared, okay, raised to negative a half, okay, all raised to power n. So in place of this fraction here, you just write this, then raised to power negative a half. Are we together, class?
Yes.
Yeah, so negative a half times n, then you have negative n over 2. That's why we have that. Okay. Then the likelihood function, the natural logarithm of the likelihood function, you remember we said L of mu sigma squared is equals to the natural logarithm of the likelihood function of mu and sigma squared. Okay, so this is the capital, that's L mu sigma squared. So when you take the natural logarithms on both sides, okay, then you're going to say, so the natural logarithm of, the natural logarithm of 2 pi sigma squared to the power of n over 2 negative, like this. When you have y is equals to exponent of, say, 2x, okay, then you introduce the natural logarithm. So natural logarithm of y is equals to natural logarithm of the exponent of 2x. 2x, did you know that? The natural logarithm of the exponent of 1. You check in your calculators if this is giving you 1. Natural logarithm of the exponent of 1. Do you get 1?
Yes.
Yeah, so that's what we have here. That's why we have this one as 2x. So same case to this point here. You see, we're introducing natural logarithms. So this one, we're saying times or plus the natural logarithm of exponent of negative sum I from 1 to n of yi minus mu squared all over 2 sigma squared. So the natural logarithm of exponent of this will simply give us the power of the exponent. Okay, that's why we have this term here. Okay, after taking the natural logarithms. So there is this minus, so it becomes minus, as you can see here. So what we are going to do next is to carry out the partial derivatives of the natural logarithm of the likelihood function with respect to the two parameters. So you remember we have two parameters, mu and sigma squared. So if we want to find the MLE of mu, then we partially differentiate the log likelihood function with respect to mu. Then we ignore sigma. So let's differentiate this function with respect to mu. Okay, we differentiate that function with respect to mu. So do we have a mu in the first term? So you see we are saying dl of mu sigma squared like this with respect to mu. These are partial derivatives that will give us what we have here. We call it L prime of mu. We don't have, isn't it? So when you have y is equals to 4 and you are differentiating y with respect to x, what do you get? Is that 0? Yes? You are differentiating a constant with respect to a variable. So that will give us 0 here, isn't it? So we don't have mu here. So when we differentiate that term with respect to mu, we get 0. We don't have mu here. Differentiate that term, this term here with respect to mu, you also get 0. You understand? Yes? So L prime of mu, we differentiate this term. There is mu here. So this is a term which is of interest to us. So we're going to differentiate this with respect to mu. So first of all, you get that mu. That's the power of the exponent here, the power of this term. Then there is this minus. So minus 2 divided by 2 sigma squared, okay, times when you differentiate minus mu with respect to mu, what do you get? Alan, you're differentiating this term here with respect to mu. What do you get? Do you get minus 1? Can you hear me?
Yes, we can hear you.
Yes.
But you are not responding to my question. We are differentiating this term here. With, what do you think? So we have negative 1. Then the sum, okay, yi minus mu, the power reduced by 1. So raised to 2 minus 1, okay? Because this is minus 2 times minus 1, that's positive 2 divided by 2 sigma squared. So of course, 1 over sigma squared times the sum yi minus mu is equals to 0. So you can cross multiply. So you have sigma squared times 0 is equals to, so you have sum yi minus mu is equals to sigma squared times 0. So any number you multiply any number by 0, you get 0. So what do you get? Sum of yi minus mu is equals to 0. That's how we arrived at this point. Are you following?
Oh, yes.
Yeah, and if you can open this bracket here, so you have the sum yi minus mu is equals to 0. So let's open the brackets. So we have the sum of yi, of course, I from 1 to n minus the sum I from 1 to n of mu is equals to 0. Okay. So you're summing a constant n times here. You're summing a constant, mu is a constant, so you are summing it n times. So mu plus mu n times. What do you have? N mu. The same way if you say 4 plus 4 plus 4 3 times, is that the same as 4 times 3? Yes. So which is what we have there. So
Yes.
we have the sum yi I from 1 to n minus n mu is equals to 0. Okay. So we can take this to the other side of the equation, the right hand side. So we have n mu is equals to the sum I from 1 to n of yi. Okay. Divide both sides by n. Divide both sides by n. N and n cancel. Population mean mu is the sample mean. Okay. So what do you have? Y bar. So this is the estimator, which of course is unbiased, because we've shown several times that the sample mean is an unbiased estimator of the finite population mean mu. Okay, so that is what we have. So we want to get the maximum likelihood estimator of the finite population mean mu. So what we do, because we cannot tell whether this one is maximum, okay, whether this estimator is maximum. So what we do, we differentiate once again this function here, okay, the log likelihood function. So you differentiate it once more, okay. So this is L prime of mu is equals to 1 over sigma squared times the sum yi minus mu is actually equals to 0. So what we want to do is to differentiate it once more. So L prime mu is equals to 1 over sigma squared, the sum yi minus mu, okay. So L prime prime of mu respect to mu. So we have minus 1 after differentiating that function with respect to mu. This is minus mu, so we get minus 1, okay, by sigma squared times the sum, okay. This is yi minus mu, okay, raised to 1 minus 1. So what do you get there? You get negative, isn't it? By virtue of this negative being here over sigma squared, whatever we have here, we know this is less than 0, isn't it? Because that is negative. You understand?
Yes.
That is what we want to show. We want to show that if the second, the first one is maximum. So then we can conclude and say the maximum likelihood estimator of the parameter mu is y bar, okay, which is given by this. That is what we call the MLE of the maximum likelihood estimator of the finite population mean mu. So you can see this is negative. It's less than 0. Okay. So how we arrive at that is by saying 1 minus 1 here. So any number raised to 0 is 1. So you are summing this plus 1 n times. So that's n times 1, which is n. So you get n over sigma squared. And the most important thing is that that is negative. So that enables us to conclude that is less than 0. Okay, so meaning that the first derivative, or rather this equation here, will give us the maximum value of the estimator. We call it maximum likelihood estimator. So what about the variance sigma squared? Okay, so you want to differentiate that log likelihood function. This one, this is what you want to differentiate with respect to sigma squared. Okay, so we have negative that's L of mu, okay, times logarithm of 2 pi sigma squared, okay, minus, what do you have? Can you write down that minus n over 2 logarithm of 2 pi minus n over 2 natural logarithm of, that's natural logarithm ln, natural logarithm of, is it sigma squared? This is the function we want to differentiate, this one. So negative n by 2 natural logarithm of 2 pi minus n by 2 natural logarithm of sigma squared. Okay. Yes. Okay. Sigma squared minus, what do we have here? 1 over 2 sigma squared times the sum yi minus mu squared. Is that what we have? Yes, class?
Yes.
Yes, yi minus mu sigma squared. We want to get the right term to differentiate. Yes, that is what we want to differentiate. So now we are doing partial derivative of sigma squared with respect to the likelihood function. So we are saying dl mu of sigma squared partially with respect to sigma squared, because we're interested in the estimator of the variance. So we don't have sigma here in the first term. We don't have sigma, so that will be 0 when we differentiate this function with respect to sigma. What about this one here? What do we get here when we differentiate this term with respect to sigma squared? Yes, we get negative n divided by 2 sigma squared. You remember y is equal to natural logarithm of x, y prime, that's the y. Same case to this other one here. This is natural logarithm of sigma squared. So we get negative n over 2 sigma squared. Then we differentiate this term, 1 over 2 sigma squared. Is that the same as sigma squared raised to power 1 divided by 2? Yes? Are we together? So this is, we are talking about the last term here, this one, okay? So that's negative, you can say that's negative sigma squared to power 1 mu squared. So when we differentiate with respect to sigma squared, then we have, so this negative 1 here, you bring it here, so negative 1, okay? times this negative here, then sigma squared, the power reduces by 1, so we have -2 divided by 2. A negative times a negative, that's a positive. So we have here sigma squared, that's sigma 2 power -4 divided by 2. So that's 1/2 sigma raised to power 4. That's why we have this one here. You understand? Do you get that?
Yes.
Yeah. So then we have yi minus mu squared, okay, is equals to 0. So the first derivative will always give us the gradient function that is equals to 0. Okay. So you can make n the subject of the formula. Okay. So you see, you can multiply both sides by, or you can take this guy to the right hand side of the equation. So you have n, then you'll have n/2 sigma squared is equals to 1/2 sigma to power 4, the sum yi minus mu squared. Okay, when you take this to the right hand side or bring this to the left hand side of the equation. So then you simplify. So these two and these two cancels. Sigma squared, okay, sigma squared cancels with sigma squared. Sigma power 4, that's the same as sigma squared times sigma squared. So one of these cancels with what we have on the left hand side. So then n is equals to 1/sigma squared times the sum yi minus mu squared. Okay. So can you get the second derivative? Can you get the second derivative of this function and show that this one will give us the maximum likelihood estimation? So when you differentiate this term once again, what do you get with respect to sigma squared? So you can do that as an exercise. And write down the maximum sigma squared. We can continue. Can we stop there for today?
Yes, we can.
So we shall continue from example number 3 in our next class. I'm sorry, I'm tired. I've been in class since morning. Have a good day.
Thank you.
Thank you.
Welcome.